So how do we monitor this power quality to do what we need to do to correct or to remove these issues that are in our system? So we have the power quality analyzers. Okay, the power quality analyzer will help us to look at the power system, know what is actually happening in the power system, what kind of power quality issues that is plaguing our system or that are plaguing our system, and that will give us an idea as to what to do in order to make our power system to be more reliable, and thus our electric motor system to be more reliable. Okay, so this is the Fluke product. As you can see, this is the power quality analyzer that is connected to an electric motor supply circuit. Okay, so this will give us the voltage and current events over time. Okay, so if there are any issues, the probable cause of that particular issue on the system, from the analysis of what the event log will be able to ascertain or zero in on what the problem actually is. Okay, so this meter can help us to look at the current and voltage, the root mean square values, as we saw earlier in when we were looking at unbalanced voltage. Okay, it will also help us to look at the phase relationship. We also saw it earlier, whether the phase relationship between the three phases of our power system or power supply is normal. Okay, even the current relationship, we also look at it. We also see it. Power factor and the frequency of operations, we'll see them. Then the active, reactive, and the apparent power. Okay, we'll see them so that we'll have an idea of the usable power and even what to do in order to correct the power factor in our system. The active energy, the reactive energy, and the apparent energy all will be clearly seen in the analyzer. Then the harmonic distortion. Okay, we can remember, like we saw earlier, we saw that so many other voltage signal, okay, that are integer, that have frequencies that are integer multiple of the fundamental frequencies, they are superimposed into the fundamental waveform and thereby distorting it. So with this meter, this analyzer, we'll be able to carry out what is called the fast Fourier transformation, known as FFT. So with the fast Fourier transformation, we'll be able to separate all of these signals according to their frequencies of occurrence. Okay, so we'll see the contribution of each of these harmonics into the distortion in the process. So we'll see the harmonic spectrum and be able to know which of them is causing the problem in our system. So this is how the quality analyzer is connected to the system. Okay, so this now we can actually place this in two ways. We can place it at the input into our facility, where power system interfaces with our facility. Are we getting it? So that we will know if what is entering the system is of the required quality. Then we can also have it connected or placed to our load, that is the electric motor load on the feeder line. So what this means is that we can place it upstream of our circuit breaker. When we place it upstream of our circuit breaker, of course, we'll see everything that is happening within that feeder line, okay, on the system. So we have 4 current probe in most cases. But if you have a direct 3-phase equipment or 3-phase line, you connect the 3 current probe, okay, as shown on the diagram on the left. Then we have also 3 potential probe. It is usually 4, 1 on the neutral. Are we getting it? So you have those 3 potential probe on each of the phases 2 to give you the potential reading on the analyzer. So this is the current probe and these are the potential leads. Okay, so you see you having this for earth, neutral, line 1, line 2, line 3, also neutral, line 1, line 2, line 3. Okay, so that is what you are seeing on your screen now. Okay, that is what you are seeing on your screen now. These are the input of the current input, as you can see here, and these are the potential input, line 1, line 2, line 3, then neutral, as you can see. Okay, so these probes, you fix them here, 1, 2, 3. Then these probes, you fix them here, 1, 2, 3. Okay, and neutral. So the probe that you have here and here, you must take them to line 1. Are we getting it? Then the probes that you have here, the potential at the current probe, must take them to line 2. Then here, the potential at the current probe, you take them to line 3. Then here, the potential at the current probe, you take them to the neutral connection. Okay, so you can actually set it and leave it, and then for the equipment or the analyzer to collect information for you for over some time. Or you can look at what is happening in the system real time to know how the system is actually behaving as you are monitoring the system. Okay, so this is what the analyzer look like. So you see that you have the voltage and the phase information as we saw earlier, and the phasor diagram. So this is the waveform, current and voltage waveform. Okay, this current and voltage waveform, as you can see, to the untrained eye, it actually makes no sense. It looks confusing. Are we getting it? So remember, we are having this kind of waveform because we have harmonics in the system that distorted or that is distorting the normal wave sinusoidal waveform. What you are seeing here now is not sinusoidal. So to help us to have a good sense of what we are seeing, although we can determine the voltage levels and the current levels from what we are seeing at different times. Okay, so we'll know when we have the peak consumption or the highest current and voltage event. Are we getting it on the system, or the lowest? They are clearly visible, the dips and the heights, you understand? Or let me say the valleys and the highs on this graph. But to enable it make some sense to us, we can press the harmonic button on the analyzer. As you can see here, this is harmonics. Okay, if you press it, you have something like this. So you see that it has separated all those waveforms that is causing that distortion into their various frequency of occurrence. Okay, so as you can see here, we have the fundamental frequency, which is 1 times the frequency. Then the 2 times, there is no frequency. As you can see, there is no occurrence here, as you can see. Then we have at the 3 times, we have at the 5 times, 7 times. Okay, so if you look at the magnitude, you see that the magnitude, they are not so great. Are we getting it? The magnitude are not so great, and that is why we have this minimal unbalance. Okay, as you can see here, the unbalance is not too much. If we calculate it now, the meter itself can also give us the unbalance. Okay, so look at the total harmonic distortion on each of the phases. We have it 3.4, 2.1, and 1, which is okay, which is acceptable. Okay, you know, if you are looking at the input from your utility, it is advised or it's recommended that the total harmonic distortion should not be more than 8% at the point of input. Okay, if it is more than 8%, of course, you inform your utility to do whatever they need to do to reduce the distortion, harmonic distortion. So as you go into your system too, remember those nonlinear loads that we have in our system that helps us to improve the life, okay, that helps us to improve our operations. They also have the effect of introducing such harmonics that will become problematic if we do not take care of them. Okay, so when such happens, we also see them in the system as we are monitoring or as we are moving away from the input point or the point of common coupling between your facility and the utility. So this gives us the beauty. Okay, remember these harmonics, these triplet harmonics, 3, 9, 15, 15, and 27, they are the most problematic harmonics. Okay, those remember these harmonics, we have those that are positive sequence. Okay, those positive sequence, they generate magnetic field, especially when they go into your electric motor, that are in the same sequence with the magnetic field generated in the electric motor unit. That is, they rotate in the same direction, simply put, so they will not affect it. While negative sequence, which are the even integer multiple, that is 2, 4, and the rest, okay, what they do is that since they are negative, they act against the magnetic field that is created by the normal phase rotation of the voltage that you need to run your electric motor. So that will kind of affect the efficiency of the electric motor. But those triplets, zero sequence harmonics, they behave like single phase load. You remember, if you do not balance up the phases, okay, the load on each of the phases, what will happen? You see that you have current flowing on your neutral. Are we getting it? So if you have those triplets, they will tend to add up, since they will not cancel out, they will tend to add up on the neutral and cause neutral overheating. Okay, and also within the electric motor system also, they cause a lot of overheating if they go into the system and into your electric motor system, cause a lot of overheating in the electric motor system that will eventually affect the integrity of so the harmonics, we need to guide against, okay, those harmonics as they come into the system. Then, as you can see, also the transients can also be shown by this analyzer. So those transient events, okay, those voltage spikes that we have, maybe as a result of lightning or what have you, all of them will be clearly shown in the analyzer. So when it happens, and maybe if there are some failures that occur at that point, we will know clearly that that is precisely what caused that failure. Okay, and as we well know, all of this can cause insulation breakdown and shorting of phases or windings, and eventual destruction of our electric motor or the line. supplying our electric motor. So